Okay, yeah. You should be seeing my screen.
Yes.
Okay, ready. So good morning. Okay, so good morning, everyone. My name is Livia Lestingi, and today we'll present to you the work that I'm carrying out for my PhD at Politecnico di Milano, under the supervision of Professor Rossi and co-supervision of Professor Bersani and Dr. Oscar Pur. So to introduce the topic, let me give you a few details on the motivations and the context behind my research. So as the title suggested, the context of my research is the future evolution of robotics. So robots historically have been mostly found in industrial settings, but they are now quickly spreading to everyday settings such as healthcare, home assistance, entertainment, and so on and so forth. So the main distinguishing feature between all these different settings is that these are much less constrained and much less predictable environments, mostly due to the large presence of humans that robots have to interact with. So to deal with this kind of unpredictability, right now there's a number of technologies that have already been developed and deployed, such as to deal with the unpredictability, such as collision avoidance, task reallocation, etc. But these are mostly reconfiguration strategies that happen online at real time. So to actually achieve more supportive and robust interactive applications, we need solutions at an early design stage of the application itself. So from a software, let's say from a software engineering point of view, which is the issue that my work addresses. So the very high level goal of my research is to develop a model-driven framework to analyze and develop interactive robotic applications that by design can handle the unpredictability of human behavior without losing the robustness, so with the guarantees that we get from formal verification techniques. So in the rest of my presentation, I will introduce each of, let's say, the contributions of my framework in more detail. To give you a quick high-level overview, the entry point of my framework is a model of the interactive scenario, so the human-robot interaction scenario. We put the model through verification, so we exploit verification techniques to estimate the most likely outcome of the scenario. If the results are found to be satisfactory, the application can then be either deployed or simulated. So it moves forward to runtime. And finally, we exploit the data collected at runtime to automatically adjust part of the model and iterate the procedure if this is found to be necessary. So to start with the first module of the framework, as I mentioned earlier, the main point is it deals with the formal modeling and verification part. So the main question that it tries to address is how can we model the system? So how can we specify how many agents we have, their characteristics, which services they are requesting, etc., and so on and so forth. So to produce a formal model, the first choice that we had to make was to choose the formalism that most suited our needs. So the set of requirements that we identified was we wanted our model to capture how the agent's behavior varies depending on their state. By agents, I mean the humans and the robots in our scenario. We also wanted our model to capture timely synchronization between the different agents that are at play, because clearly we want the analysis to encompass the interaction between the humans and the robot. It was important for us to also include a model of the relevant physical variables that we have in our system, such as the robot's battery, or we also have a model of human physical fatigue, as we usually we have use cases from the healthcare scenario where people are usually in critical physical conditions. So this was also very important. And as I mentioned earlier, a big, let's say, selling point of the work is that we capture the unpredictability of human behavior. So this also had to be part of the model as well. So the combination of these requirements led us to the choice of a state-based formalism, so specifically automata, specifically a network of automata that interact with each other, that synchronize with each other. Since for the physical variable requirement, we chose hybrid automata that allow us to express generic constraints on clocks that result in generic sets of differential equations. And finally, we chose to approximate the unpredictability of human behavior with stochastic features. So the result is what we call stochastic hybrid automata, which I will refer to as SHA in the rest of my presentation. So to start drawing the workflow of my framework, the first module that I'm presenting right now is what we call design time module, so the analysis that occurs offline. And the first building block is indeed the formal model of our system. So once we have developed our formal model, clearly we want to run some verification with it. And since we have a stochastic model, we chose as a verification technique statistical model checking, of which you see the workflow in this slide right here. So the main fundamental ingredient, of course, is the model that is to be put through verification, which is the SHA network that I described to you right now. Clearly, the second main element is the property that we want to verify. And in this case, the choice, which is also kind of induced by the tool that we use, is to use PCTL notation, which is probabilistic computation tree logic notation, which allows us to express quantitative constraints on the probability. So we verify the probability that a certain property will hold for our system within a certain time bound. So the further main requirement of SMC is that we have samples available of our system. So we have traces available, or traces or runs of our system. And in our case, to generate traces, we use the UPAL SMC, the UPAL tool, and specifically its extension to SMC, which is also the same tool that we use to develop and maintain our model. So what happens once these traces are generated, depending on how the properties specified, SMC runs either hypothesis testing or estimation. So the results are different depending on the technique that is used. So if hypothesis testing is run, the result will be a Boolean saying whether the probability of the property holding within a certain time bound is greater or not than a certain threshold. If estimation is performed, which is what we do in our case, the tool will return a probability range of the specified property holding within the specified time bound. So to keep filling our workflow, we also have our property. In our specific case, we want to verify the probability that the robotic mission will end with success within a certain time bound. Then statistical model checking is performed, and the user in charge of designing the application is then in charge of assessing whether the obtained results are acceptable or not. If they are not, they can modify the parameters of the scenario and iterate the procedure if necessary. So to take a look at my research plan, developing the design time module and testing it was the main activity that I carried out during my first year of PhD. To move on, so with the second module and second contribution of my work, the second question that we wanted to address was so once the application is found to be ready for deployment, how can we ensure that what we verified at runtime is still holds at that we verify that design time still holds at runtime. So to this end, I have developed the second module of my framework, which is what I call the deployment module, whose entry point is a principle to map each feature of the automata to features of what we call deployment units, which are executable pieces of code that replicate the behavior of the agents that we have in our network. So humans, robots, and the controller, so the orchestrator, which is in charge of making decisions about the system. So the result of the application of this principle is that we have an executable version of the controller, which is in charge of receiving data and making and sending commands to the agents if necessary. As for the agents themselves, so as for the deployment environment, so far I have been working with a fully virtual deployment environment. So with simulated humans and simulated robots in a 3D simulator environment. Right now, I'm working on a hybrid, let's say, deployment environment. So I have a physical robotic device which interacts with virtual human agents in the simulated scene. In both cases, the controller and the agents interact with each other over a middleware layer, which is based on ROS. So it is a network of ROS publish and subscriber nodes. So the main outcome of the deployment module is that we, besides running or simulating the application, we get to collect a bunch of system traces of how our system behaves at runtime. So again, to update my research plan, the situation at the, so actually the developing and testing the deployment module was the activity that I carried out between the end of my first year and the start of my second year. As for what came next, so for the third and so far final module of my framework, which is what the one that deals with automata learning that was also previously discussed. So the question that comes naturally now is, we have a mapping principle that gives us some guarantees that the controllable parts of our system, which are the orchestrator and the robots, will behave at runtime as we design them, as we model them at design time as their formal model. As for the human, of course, we have zero control on their behavior. So we cannot be sure that their behavior at runtime will be the same as their formal model. So what happens if we run into this case? So what happens if human behavior that we observe at runtime is different than their formal model? So this means that the estimations that we obtained are no longer actually accurate. So what can we do? So what we did to try to address this issue is to develop an active automata learning algorithm, which we call LSHA star. When I say developed, I don't mean completely from scratch. As the name suggests, we actually extended the infrastructure of an automata learning algorithm, which is actually well established in literature, which is LSAR, which actually returns, which is able to learn deterministic finite automata. So we had to extend this to so that it can cover our own formalism, which is stochastic and hybrid. So it needed to be extended to also to learn the feature that we need in our specific case, so the hybrid and stochastic ones. From a high level point of view, the goal of this phase is that we exploit the traces that we have collected at runtime to learn an automaton modeling human behavior, which is at least aligned with the knowledge that we have so far accumulated about the system. So which is at least up to date with the collected observations. Once we have the, let's say, updated human modeling automaton, this is plugged back into the SHN network to repeat the design time analysis and hopefully obtain more accurate estimations. So to complete, let's say, the workflow, which gives us a general overview of my work, the one that I just described to you is the third and final phase, which is what we refer to as model adjustment module, whose main block is clearly the learning algorithm. Of course, there's the data that we collect at runtime. So the signals that have been recorded by the sensors need to be processed to be first to be fed to the learning algorithm. And the main outcome is the updated model of human behavior, which, as you can see, there's a sort of feedback loop that plugs it back into the formal model to repeat the procedure from the design time analysis. So this concludes, let's say, the technical, the presentation of the technical details of my work. To give you an overview of the current status, let's say, of my research plan. I just started my third year, actually. So this is the situation more or less how it was 1 month ago about. Actually, as I mentioned earlier, I did develop the deployment module between the end of my first year and the start of my second, and developing and testing the adjustment module, mainly the learning algorithm, was the main activity that I carried out during my third year. As about what is going to happen next, as I mentioned earlier, I'm now validating the framework with the real robots, so this is currently underway. We would also like to improve the user friendliness of my framework by developing a domain-specific language so that users who are not expert in formal modeling can configure their scenarios in a more accessible way. We're also working on extending the framework to multi-robot scenarios. And finally, it would also be interesting to extend the framework in a more extensive way by developing a procedure to automatically compute alternative mission plans for the user to choose from, which is now done manually. And it would also be interesting to develop a procedure to synthesize the controller or at least feature it automatically so that it evolves along with the evolving system, which is evolving due to the learning phase. So this will be the main activities that I will carry out during my third and final year, besides clearly spending the last months on actually writing the thesis. So thank you for your attention.
Thank you for your presentation. That was a really nice presentation, I think. I like the structure and the way you gave your motivation and gave us high-level overviews at each turn. So in your future work, you mentioned, oh no, is there anyone who has questions first?
I have a comment here. I also like the presentation a lot, and what I liked in particular is the setting the scene in the beginning of kind of that the research questions have the context. So that was very well done.
Also, the workflow slide where you didn't show everything at once, but showed things when you were talking about them is a really good way to do things, I think. Mm-hmm. Yeah.
Thank you.
I think Raman now wants to say something.
Oh, yeah, thank you for the excellent talk. I just have a naive question. So in the adjustment module phase, you're learning human behavior, right? Or you're learning a model of human behavior. Does this mean that you can avoid formalizing that in the design time module? So avoiding any conditions about what the humans are actually doing?
Okay, so good question. So the workflow here, the workflow with which I developed was that I initially created, let's say, an initial version of the human behavior manually. So the first automaton was manually drawn by me, let's say. But the idea is that that can be, let's say, the model which is used for the iteration 0 of the framework. But the idea is then with the further iterations of the framework, the model which is learned and which can be also different from the first one, which is learned through the learning algorithm, will be then will replace the original version within the SHN network. So let's say the model for iteration 0 is manually drawn and then it is automatically updated.
Okay, thank you.
Okay. So for your form, let's see, are there any other questions? No. For your form model, here you're using Automata directly. Is there any, did you consider using something more like synthesizing from properties somehow? But I guess it's difficult to do it in the
It's not easy also because we have, as I described to you earlier, we have quite a rich set of features. So these are complex models to be automatically synthesized. What we plan on doing is at least, let's say, isolate the parts of the model which are, let's say, fixed and the parts that are at least customizable based on parameters. So we are planning on at least not generating a model from scratch, but partially customizing it based on user input. So that's what we aim to do in this method.
Yeah, that sounds reasonable. Good. If there are no other questions, we can move on to the next speaker. Thank you very much.